thank you all for the opportunity today to talk about a favorite topic of mine. My background is applied physics and engineering, and so I really want to talk a little bit about entropy, thermodynamics, and spirituality, and all this cool stuff here as well. So let me just prepare this. Okay. The good type of ice. Okay. All right. Yeah, it's going to be relentless. All right. So imagine you're holding an ice cube. And in fact, I remember as you were guiding us today, you did bring up water and ice as well, Nat.
Preparing them for your presentation.
Exactly, right. So I've got a few pieces of ice here, and so I'm going to share at least on the front row. So aren't you glad you sat in the front row? Yeah. And the others will just have to imagine it. Here we go. Here we go. Great. Excellent. So imagine you're holding a piece of ice. Now, really feel it for the first time in a way you haven't felt it before. So go ahead and for those in the first row. So I didn't have enough ice for everybody. It's a precious commodity, you know. So anyway, so you're holding this ice in your hand, and close your eyes and imagine feeling it. What are some of the things that come up for you as you're feeling it?
Cold.
Yes. Wet. Dense. Hard. Yeah. And now it's dripping as well, right? Yes. So something's happening here, right? This ice is not remaining constant. You guys all agree with that? It's melting. Now that seems really intuitive, but really pay attention to this for the first time almost. This ice is melting. It's going through change, right? It's not permanent. It's impermanent. It melts into water, right? Go ahead and pour it back into the container. Boy, my hands are really cold now, but okay. So you're feeling that ice, and you notice it's going through transition. And that essentially is what thermodynamics is about. I know that sounds like a really scary word, you know, from the Greek, thermos, heat energy, and dynamic, which means like force or power, which causes something to move, something to happen, right? But don't worry about those fancy words, and then we'll get into entropy. And I've been kind of thinking about this for some period of my life, about how does it relate to spirituality as well. I want to give a demonstration. So that was cold water. Now we have hot water right here, okay? This is quite hot. And I have what here is called a Stirling engine. Some of you guys who have physics or engineering background may be familiar with this as well. So a Stirling engine is quite different than an internal combustion engine. So what will happen if I spin it? What eventually happens to that? It stops, right? So it doesn't go on forever. It's impermanent, right? It stops at some point. Better stop, all right. So there you go, right? There's no batteries, there's nothing in here. So it stops. Why does it stop? Right, which causes what? Which causes energy loss or heat. So that energy that I put in, the kinetic energy, has been converted, transmuted to, to emotional energy, and then finally to friction. So then it all stops. But I have here hot water, okay, and I'm going to put ouch, yeah. So I'm going to put it on here, let it warm up just a little bit, okay, and then I'll give it a little bit of a nudge, and let's see what happens. This better work, okay. All right, so let it warm up. Okay. And I think it's going to take, it's hot. So it's going to take a little bit of time for it to transmit the heat. Oops, sorry. Okay. Let me just reassemble it. There we go, okay. Nothing like live engineering, right? So, yeah, that's it, good. All right, so I'm going to feel that temperature. Okay. Seems to be getting some resistance right now. Yeah. Okay, so I'll wait for a little bit while it gets warmed up. And what's going to happen is that heat energy is going to come in here, cause a differential, and then cause this thing to turn. Okay. So I have to position it just about right. Okay. Yep. I might have broken it. Hopefully not. Okay. I'll wait for it to heat up, and then we'll see what happens after that. Okay. So you looked at ice. Ice changes, right? From a solid to a liquid at room temperature. This is a pressure cooker. So what does a pressure cooker do? It changes the pressure inside a volume, a fixed volume. And when that happens, the water heats up, but more to the point, the boiling point of the water, boiling, is now greater. So instead of at 100 Celsius, it will boil at 120 or 130 Celsius, which means that there's steam under high pressure, which means your food can cook twice or 3 times as fast, right? So that essentially is what a pressure cooker does. And I don't want to throw too much math or science at you. This is all going somewhere. But you can see here that as I change the atmospheric pressure, which is what I can also do with something like this, is I can either increase the atmospheric pressure, like in a pressure cooker, or I can decrease it. And I hope this is warm enough. Yeah. So I'm going to attempt to boil water. Okay. It may not be warm enough quite yet. Sorry for making a mess on all of this. Okay. Yeah. Okay. So this is, when I pull the syringe right here, what happens is I can effectively create a vacuum in here. And then you'll start to see bubbles appear. Can you guys see the bubbles? They're very small right now, but over time these bubbles appear, and effectively the water is boiling, but it's boiling at a lower temperature rather than at a really high temperature. Let me put this back on here. Okay. So the water may not be hot enough, actually. So what's this deal about thermodynamics, and why do we even care about it? So it was in the 1700s that people started to experiment with machines, like machines, heat engines and steam engines, and that caused the first industrial revolution. So really, thermodynamics is just about how heat and energy moves, transforms, and transfers within any closed or isolated systems. It helps you understand really how energy works. So why do you care about it? Because life is energy. Life is change, right? And thermodynamics is one of the most important sciences in engineering that helps us understand how life changes, right? And it has really helped create our modern society right now. It helps you understand the limits of efficiency and why do even machines require fuel. Helps you optimize and harness the most energy possible in your life while things tend to, quote unquote, decay or become disordered. So all the things, a lot of things you use right now, car engines, HVAC systems, chemical reactions, even life itself is based on these thermodynamic principles. It helps us even understand how stars emit the energy. You know, we're not in an isolated system here. We exist in conjunction with the sun, right? So it helps us understand how life arose, how life continues, and maybe what will happen at the end of the universe. So these are some of the key terms. Again, I don't want this to be a physics class, but just really quickly, energy, capacity to do work, heat, which is a path or a process of energy transfer, work, energy transfer between a system and surrounding, and then you hear about temperature, pressure, volume, and a really interesting word, entropy. And I think you all have an idea of what entropy is, but it's really can be a little bit elusive, and why is it relevant for us in our spiritual life as well? So there are four laws of thermodynamics. Again, I don't want to get too much bogged down in detail, but these are the colloquial interpretation of it. That is, if it looks like a thermometer, if it behaves like one, then it is a thermometer. So it's really, it defines temperature, especially when two objects, are they in equilibrium with each other or not? The first law is you can't get something for nothing. You can transfer and convert energy, but you can't get, but it'll always be lossy in some shape or form. Second is you certainly cannot break even, and that's where entropy comes in. What does that mean? And then third is you can't quit the game. That is, you cannot reach perfect order. Okay, these are the technical definitions, but I think we can kind of skip over that if you guys want to have a look at it later on. So I really want to talk a little bit about entropy and how it relates to our life. And a lot of us have used that term casually, kind of meaning disorder, chaos. Oh, I've got too much entropy in my life. My room is really messy. It's too much entropy. That's not technically what it means, but that's a result of understanding what entropy is, and I'll get to that in a moment. So it was in 1865, while the Industrial Revolution was well under its way, that Herr Rudolf Clausius was thinking of this word, Verwandlungshalt. Thank goodness the Germans don't coin words in science too much for us to use. So that was what he wanted to come up with. And he said, no, it's probably too hard for people to remember. For those of you who know a little bit of German, it can be a really interesting language when words get really, really long. So he went to Greek and said, oh, I'm going to use the word Greek for en, which means within, and trope, which means transformation or change. So it's transformation or change within. This is sounding quite interesting. All right. So it's describing the amount of energy that has changed in a usable, ordered state. But we'll get to that in a moment. I'll forget these equations. So when we talked about the ice cube before, or something that is hot, like this, energy goes from what to what? From hot to cold. But you don't really see it going from cold to hot, right? This is kind of interesting. So when I hold it in my hand is warmer, and it's being transferred to the cold of, to the cooler ice cubes, which is causing it to melt. And eventually, what happens to the ice cube? It turns into water, but it reaches an equilibrium, right? It's at the same temperature as the room, or my hand, or whatever it is, right? But my hand obviously is warmer, or at least my body, 37, 39 Celsius, 97 Fahrenheit, or whatever it is. But why is that? Why am I warmer? Well, there's a reason for that too. So one of the things this guy, when he was developing entropy, what they wanted to do in the 17 and 1800s was really look at how to make things more efficient. How can we optimize these steam engines, all these types of motors and all these sort of engines that they had? And so that's why they started to explore this concept of entropy, because it puts a limit, a theoretical limit, as to what you can really do when you convert from one to another. So when you have an engine, you have something called a heat reservoir and a cold reservoir. And energy goes from one to the other. You can then deploy it in the engine to do work, right? So energy is just the capacity to do work, like a battery has energy. But until you hook it up, it ain't doing anything, right? So this concept is really important, that there's always two differences in temperature or in states in the universe. And that's what allows everything to happen. And this is really, really interesting for life itself. You could also, in this case, it's reversible. If you put in work, like spin the motor or everything, you can go from a cold reservoir to a hot reservoir. And that's exactly how a refrigerator works. Again, not to be an engineering discussion, but you've got this incredible fluid going through in your refrigerator, which is cooling the inside of the refrigerator, but it's at an expense. It's doing something. It's moving that heat from inside to where? Just outside. So that means your kitchen actually gets warmer. So if you leave your refrigerator door open, your kitchen's going to get really, really, really warm. So it's not a good idea. So something is moving from one place to another. And this is really interesting. I think when we started to understand how things move in the universe, a lot of our sciences and engineerings are about movement of something. Movement of matter, movement of fluids, or movement of energy. And that was one of the really hard things for us to understand. And then, of course, Einstein came along in the 1900s, late 1800s, and he took that to yet another extreme. Movement closer to the speed of light, or acceleration, or if you include gravity, wow, really weird things start to happen. So in that sense, he generalized Newton's law. But, so let's see, what is entropy? Okay, technically, it's the measure of energy dispersion. How spread out is the energy at a specific temperature in a closed system? So this has two implications. How much energy is available for us to use? This is why this is important. It's not just some theoretical concept. Is how can I use that energy in whatever it is, right? Like recently we sent Artemis, right, to the moon. There were 2 rocket boosters, I believe, at least, on the sides of that rocket. That's compress oxygen and hydrogen at under really, really high pressure that it became liquid. So they lowered the entropy, so to speak, of those combustible gases. They combine it together and you get combustion. If you ignite it, and you get residue of water. But they had to do it under a high pressure in a low volume. So temperature, pressure, volume. These are really, really interesting things. But here's another interesting thing. The number of possible microscopic arrangements that correspond to a macroscopic state. Boy, that sounds really fancy. But I'll get into that in a moment, actually here. Here we have 2 things. On the left, you have something that has lowest possible entropy. It's usable energy. So imagine the red balls are something that have energy, and the blue balls have a different sort of energy or lower temperature. If you arrange it like this, you have the most usable energy in that system, right? It also looks very ordered. This is why we tend to think of entropy as a measure of order and chaos. It isn't necessarily, but things that have the most usable energy tend to be ordered like this. And so when we compress those gases in the tanks of hydrogen and oxygen, they become more and more ordered, such that they even became liquid, right? So even at not very, very low temperatures, you can make something liquid. But if you look at the right, that looks really jumbled. So there's so many ways to order that, and so that has a very high entropy. So why does this really even matter? Because energy goes from concentrated to more spread out, right? And it determines something called the arrow of time, and it may even have implications for consciousness itself. It is not by itself. See, spontaneously, it will go from concentrated to lower concentrated, from lower entropy to higher entropy. So they say, we think that when the universe began with the Big Bang, it was a really, really low entropy. How did it came to be in that state? We don't know. But it was really, really low entropy. And then it expanded. And ever since then, the universe has been going towards higher entropy. And what we're doing is we extract the energy by looking at the differences, the differential. We take higher ordered states, we extract the energy out and eject whatever in our case, metabolic waste, and that creates a high entropy. So we take the lower entropy and eject out high entropy is what I meant to say. Yeah. So it also determines what happens. On the left, you see, can you guys see it? Yeah. I put the ice in water, and it starts to melt, right? But does the opposite ever happen spontaneously? See, spontaneously, without my involvement, the ice is melting on one side, you see? But on the other, imagine from the water, ice was formed by itself. That does not occur. But if I injected energy, like in a refrigerator, that could occur. But that energy had to come from somewhere else, right? So this helps determine the one-way aspect of entropy, or of time itself, perhaps. It may help explain time to some extent. So imagine you have a coffee mug. You've got creamer on the top and coffee on the bottom. Initially, they're separated. That's low entropy. But as I shake them, I get medium entropy, but complexity arises. So what's interesting is in low entropy, often you don't have many interesting things. It's just like it's ordered, but nothing is really happening. It's in between the two, between going from really low entropy to high entropy, that interesting shit, excuse my language, happens, right? Interesting stuff really happens. Because if you look at that coffee, all these swirls and all these patterns, and the barista at Starbucks can create all these interesting things. Really interesting thing is happening. But in the end, it's just bleh. It's just merged into this liquid, right? Sure, you can drink it, it's tasty, but nothing interesting is happening there. And this has an implication of life. Because then people ask is, okay, so if things move from lower entropy, where they're really ordered, to higher entropy, where they're not quite so ordered, or the energy to use it is not really available, then how does life arise? And that's a really, really interesting question. But before we get into that, imagine an egg. You have an egg and you drop it. When that egg drops, it smashes. But will the egg by itself spontaneously reconstruct? It does not. Right? But it will shatter into many different forms or many different little particles and so on. And there are many ways to arrange that. The egg has higher entropy when it's shattered, right? Okay. So batteries, for example, when they're a full battery in your car is low entropy, but it has available energy, is high. It can power something. A dead battery has high entropy, but it has low available energy, right? Compressed gases, like the boosters of the rocket that went to around the moon, had low entropy, but as ignited, it went towards high entropy, right? So Earth itself, and going back to the question of life, and then moving on to consciousness too, is Earth is dependent a lot on the sun. Everything really, almost all the energy we use outside of, except geothermal and atomic energy, which is a different discussion, comes from the sun. Life, plants are really efficient at converting that sunlight into usable energy. And so, but remember, this didn't happen overnight. This happened over millions and millions, and if not billions of years. So it is possible to have localized low entropy, but overall the whole system is high entropy. So what happens is we get, for every visible, usable photon we get from the sun, we eject 20 high entropy, low energy photons as infrared that are not really particularly usable, as say. So life itself becomes a form, an entropy machine, right? You can localize, you can create systems where locally you have really low entropy and complexity and organization. And what's really interesting, they say life may have arisen, well, apart from the universe wanting to get to know itself, but life may have arisen as a form of a high entropy machine, because rocks don't do much for entropy. They stick around for a long time. They absorb the energy and radiate it out. But we require a ton of energy. And everything we create requires a ton of energy. And our waste, our metabolic waste, sweat and heat and 100-watt light bulb, whatever you want to say, is quite a lot. So we, in some ways, are a high entropy machine. We're actually speeding up the decay of the universe from a thermodynamics perspective. So that's really interesting. So, which will cause life to actually become even more complex, because the more complex life is, the higher entropy machine it is, the more energy it requires, and the more waste it produces. And that's really, really quite interesting. So remember, what I want you to get from this is not even so much about thermodynamics or all the science mumbo-jumbo, whatever, but really look at things as systems. Look at the interconnectedness of everything. That is really what is quite interesting. So I was thinking about entropy and Buddhism as well. One of the key aspects of Buddhism is impermanence, anicca. All things change. Remember what the Buddha's last words were? Oh, Ananda, realize that all things decay, are impermanent. Seek salvation on your own merit. So energy is constantly in motion. Everything is in motion. And thermodynamics, from a physics perspective, helps us understand that. So entropy is constantly increasing, right? And suffering, dukkha, the Four Noble Truths, the striving for stability, low entropy, is fundamentally unsatisfactory. We can never entirely overcome it unless we do something, right? So life is constantly moving towards higher entropy, disorder if you want, quote unquote, or less usable energy, if you will. So what can we do? We can realize the interconnectedness of things. Energy and entropy works within systems through interactions. This is a key point about everything I'm saying here, is that there's interaction, whether it's sangha, community, whatever it is. So Buddhism also talks about dependent origination, where nothing exists in isolation or stays the same. And then karma, energy is converted, the first law, but never destroyed. Energy and matter equivalence, if you will, with E equals mc squared, but regardless, energy is converted, never destroyed. And maybe that is the case with consciousness as well. We are moving, we inject mindfulness, we inject meditation into our practices so that we can order our mind. And maybe consciousness is a state of low entropy. And maybe nirvana, I'll leave that question to you guys. What is nirvana? That's a whole different thing. How does that fit into entropy? Now, caution, I'm talking about physics concepts, thermodynamics, and I'm using them as a metaphor for applying them to Buddhist ideas here. I'm not saying they map directly, but I find the strikings quite parallel. So the key ideas are impermanence, change. Everything is in movement, in motion, right? And in Buddhism, in meditation, we're working towards a path to inner order. We are realigning our consciousness, if you will. We are observing the thoughts that arise in this soup of energy that is within us and all around us. And we do so from an interconnectedness perspective. So I found this here about Buddhist cosmology and the parallels. Again, it's a metaphor, so take it with a grain of salt, right? There's formation, the Big Bang, if you will, low entropy. There's expansion, but there are localized pockets continue to be localized pockets of low entropy where things coalesce. Gravity, for example, does wonders. Gravity helps to create these stars, right? The matter coalesces, high pressure, high volume. Your entropy gets lower, 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 and boom, it ignites, fusion. Without the sun, without stars, there would be no universe as we know it, right? All energy, and in fact, much of matter, if not all matter, comes from the stars. So then there's destruction, right? High entropy. And there's void. And in Buddhism, we also talk about rebirth. So what happens in that nirvanic state, and how does that continue? That is a question that you guys can look at yourself, a whole discussion itself. What I really found interesting is how a lot of our science is about understanding motion and interconnectedness. There's thermodynamics and fluid dynamics that shaped the first industrial revolution. Then there was electrodynamics and quantum electrodynamics, which shaped the second, computers. And now we have information. And now we are working with information. We are getting closer and closer to consciousness in terms of data and information. And special and general relativity is a generalization of Newton's laws, if you will, right? All of these things have something in common, and they are about movement. They are about force. They are about power. They are about change and understanding that. And in terms of knowledge and science in general, outside of psychology and meditation, that I think can help improve our lives, these are kind of three areas that I'm doing more research in. And I would say risk decision-making and game theory is a fabulous area to look into if you haven't looked into it. There was a great film, John Nash, was it? A Beautiful Mind, and about the founder of game theory. And it's really fundamentally about decision-making, because in life we are constantly making decisions. How do we make those decisions when we consider other factors and other people? And that's what game theory is, and that's what risk management is about. Complexity in systems. There's a great place I went to in Santa Fe last year called the Santa Fe Institute of Complexity. And that's about understanding emergent properties, that systems, when they integrate and work together, different things arise than when they were just individual components and part. So that is a new area, an area of research and science that is really, really critical, is complexity and systems. And of course, artificial intelligence. You guys know about the different things like Claude or ChatGPT. I think one of the key things that will arise from all of this is beyond just a really useful tool, whether you want to write emails or whatever, I think it will help us understand the nature of consciousness itself. Because that, to me, is one of the last great frontiers that we have. And it's right here. What is consciousness? Where does it reside? Is it an emergent property? And the implications for that, for nirvana, for meditation, are immense. And as the machines we create get smarter, quote unquote, or more knowledgeable, there's that one area that I think will remain elusive to them, and that is consciousness itself. And that is an opportunity for us to use all this knowledge and our sciences to probe not only the outside world, but to come back and probe in the inside world and understand what is consciousness itself. And here's a Venn diagram that I think, if you want to understand different things in life, that could help you as it relates to Buddhism, and the intersection between them. Strategy, decision-making, and so on are very important. But I'd like to leave you with, and we're half an hour up now, kind of key points. So thermodynamics helps us understand movement of energy and how we can use it, and how this all operates in the context of a system. Entropy is a measure of how spread out energy is, and so consequently, how ordered something is in terms of availability for us to use. And then Buddhism has many points of intersection with thermodynamics and entropy, but ultimately, it's a path of inner probing, right? We probe outside, only then to come back and probe inside. And I'd like to leave you with a poem, Thermodynamics and Salah. So first law, energy moves but never dies. It shifts and forms before our eyes. From heat to work, a balance kept, while through the universe it swept. In change of state of this energy, no free lunch there is to be. But systems tend towards the fray as order breaks and slips away. The universe demands more mess. It loves the chaos, more or less. Entropy grows, the final price. You cannot break even twice. As heat flows down to make things colder, and time makes all things surely older, the cold moves towards the warm in vain. a flow that will not reverse again. At absolute zero, the stillness is deep, but that is a promise we cannot keep. And finally, as each and every one of you journey through life, hot and cold, with conscious choice, you break the mold. Arrangements many via entropy allow you to peer and deeply see how letting go opens the windows of the mind as you manifest in compassion and feel in kind. Thank you. The last part, yes. The last one, yes. Thank you.